So our last section of Chapter 9 is going to be on cubic functions. We spent the rest of Chapter 9 working on quadratic functions, and so it's a little weird to be switching gears to cubic functions right at the end. But the idea is you were able to extend what you learned about linear functions into quadratics, and now we're going to extend what we've learned about quadratics into cubics, just as a very brief introduction to get the idea of what it is. So first we want to ask ourselves, what is the equation for a cubic? Well, if you take something and you cube it, that means you multiply it by itself 3 times. So our equation would be y equals x to the third power, which is the same as x times x times x. And so this is very closely related to volume, because when you're looking at the shape of a cube, if you have an actual cube, the volume of a cube, as the name suggests, you have volume equals side length to the third power. And so this equation, y equals x cubed, is the equation for the volume of a cube, and is closely related to the volume of lots of other objects as well, because volume is 3-dimensional, and when you take something to the third power, that's representing all 3 dimensions. So some properties of this cubic function. One of the properties is if you put in positive numbers in, so if you put a positive number in, what do you think you will get out? Well, when you take a positive number and you multiply it by itself 3 times, you're going to get out a positive number. What happens if you put in a negative number? With a quadratic equation, you always got a positive number out, whether you put in positive or negative. It was symmetrical over the y-axis. But with a cubic, because you're multiplying an odd number of times, you're going to get a negative number out. So it's not symmetrical over the x-axis. Some other things are, if you put in a number less than 1, what are you going to get out? When you take a number less than 1, either positive or negative, and you multiply it by itself, it gets smaller. The output is smaller. Sorry, my handwriting is messy. I haven't done this for a while. And then if you do something more than 1, the output grows really, really quickly. So if you put in a 2, 2 to the third power is already 8. If you put in a 3, 3 to the third power is 27. So the numbers are going to get very big very fast. So your output is going to get very large very quickly. So these are just some general, this is by no means comprehensive, these are just some general ideas about what a cubic function is. And the input will be taken to the third power to get the output. Okay, I want to briefly mention, especially in terms of the volume over here, that you can always work backwards. If you know the side length and you want to find the volume, you just do the normal thing, you take it to the third power. But it's also frequently the case that you know the volume and you want to find the side length. So if you take the cube root of both sides of this equation, you get the cube root of the volume equals the side length. So cube roots are the opposite of cubing it in just the same way that a square root is the opposite of squaring it. And on your calculator you either have a cube root button, or if we've covered fractional exponents, this is the same as volume to the 1/3 power. So you can use a fractional exponent instead of a cube root to find the side length. Okay, now let's move on and take a look at the graph and some data points. So what are some values? Let's make an XY table. So we've got x, and then we've got y as the output equals x cubed. So let's do some symbols. If you put in x is 0, 0 cubed is 0. If you put in 1, 1 to the third power is 1. 2 to the third power is 8. And 3 to the third power is 27. Then let's try negatives. If you put in -1, you get -1, because -1 cubed. -2 is going to be -8. And -3 is going to be -27. So you notice the numbers came out the same, whether it's positive or negative. They're just the same sign output as input. So the graph is actually symmetrical over the origin. If you make x and y both opposite sign, then that point will be corresponding on the graph. So we've got the point 0, 0. Let's plot that. 1, 1. Over 2, up 8. So 1, 2, 3, 4, 5, 6, 7. Up 8 would be like right here. And over 3, up 27 is way up there somewhere. So this graph, it's kind of like a parabola. It's curling upward, but it's much steeper. Remember, a parabola would have been over 1, up 1, but then over 2, up 4, over 3, up 9. So it's like a parabola, but it's a lot steeper. Then on the negative side, instead of being symmetrical this way, it's symmetrical this way over the origin. So -1, -1, -2, -8, and then -3 is going to be way down there somewhere. So this is going to curl. Oops, I haven't drawn it quite well, but that point is right there. So you can see it's symmetrical over the origin. The top right and the bottom left look the same. And if you put in your side length, you'll get out your volume. So if the side length is 1, the volume is 1. If the side length is 2, volume is 8, etc. So this is just the basic idea of what a cubic function looks like. And then if you want to think about more advanced ways to deal with this, you could think about doing something like this. So what if we did y equals x plus 2 to the third power? So all of the tricks that we learned in Chapter 8 for shifting graphs left and right or up and down or reflecting them or translating them, all those things still apply. So when we replace x with x plus 2, this just means we shifted the graph 2 units to the left. So I could take this exact same picture and slide it left 2 and start it from here, and it would look like this. Same graph, but it just shifted 2 to the left. Okay, so even though it's a new graph, you can apply all the things you learned before to this graph.